All right, folks, 3-2 logarithmic functions. Okay, so today what we're going to try to do is we're going to evaluate expressions using logarithms and then sketch and analyze graphs of logarithmic functions. All right, so the first thing we're going to talk about is what a logarithmic function is. And we think of it as if we have an exponential function here, this f of x equals b to the x, this exponential function. The inverse of that is called a logarithmic function with a base b, and we denote that as log b of x. And basically what we say here is we call it log base b of x, log base b of x. I'll write that really quick just so we know that. Log base b of x is how we say that. Okay. All right. So continuing on, just a couple things to point out. If we look at the graph, like we said, they're inverses of each other. So here is the exponential function here, and then here is the inverse function there, which is a log. So logarithmic functions are the inverses of exponential functions, and they reflect over that line y equals x. So you can see that dotted line up through here. That's the reflection. So when you graph these, that's what it should look like, is kind of a reflection over the line y equals x. All right, so relating these logarithmic and exponential forms, basically some things to point out. If b is greater than 0, b is not equal to 1, and x is greater than 0, then we have these things, because if they're 1 or 0, then obviously we know that there's different, it's always 1 or always 0. So in these cases, we look at some of these things. Okay, first thing, logarithmic form. Okay, logarithmic form is written in log base b of x equals y. Okay, and so you have the base being the b value here, and you have an exponent, which is y. So keep those in mind as we say if and only if here, if and only if. In exponential form, they're the same thing, just written differently. So in exponential form, our b, our base, becomes here, and then y is the exponent, right? So that's going to go b to the y equals the x exponent. So just written a little bit different. All right, each logarithmic equation corresponds to an equivalent exponential equation. So that's what we're seeing above. As we can look at it right here. Okay, that's what that says. So when we have these y equals, if we have something written as y equals log base a of x, it's equivalent to a to the y power equals x. So they all have that similarity from that box. So our first practice problems here are just going to involve sort of rewriting them from exponential form into logarithmic form and vice versa. So if we're taking this is in logarithmic form, we want to write it in exponential form. So we basically want to go from here to here, right? So when we look at these, we can see that, remember, exponential form is b to the y equals x. That's what we want to write it in. So we just kind of label our stuff here. We know from the above table that that's our b value. And we also know that this is our x value, and then this is our y value. And I'm just getting that from this place right here. Okay? So I want to move it to the other side. I've got my values there. So now I just rewrite it in this form here, b to the y equals x. So it would actually be 125 to the 2/3 power equals 25. Okay, same thing going the other way, right? I want to get it into this form, b to the y equals x. So what are my b, y's, and x's? My b is here, my y is over here, and my x is right here. So if I rewrite that, it's going to be 8 is my base to the 1/3 power, that's my y, equals 2. Now those make sense as well, because if you take a look at this, That's basically saying the cubed root, 8 to the 1/3, is the same as the cubed root of 8. So what is the cubed root of 8? We know it's 2. Same thing over here. You're taking the cubed root of 125 squared. If you did that, you get 25. All right. Now we're going backwards. Now we're going from exponential form into logarithmic form. So now we're going to go from here, and we're going to go back to that form, logarithmic form. All right, so doing so, we're going to look and say, all right, if we've got 4 to the 3rd power equals 64, well, we know that we want to put it into logarithmic form. So we know we want it to look like this. Log base b of x equals y. That's what we want to look like. We want it to be in logarithmic form. So again, what are these things? We've got the b, this is the y, and this is our x. So whatever way we can do that just to memorize these two forms is going to be huge, because now I can just plug it in there and it's really not an issue. So now when I do this, it's log of b. Well, my b value was 4, so log base 4 of x, which was 64, equals my y of 3. Okay, over here, the same thing, right? We want to have this as my b, this is my y value, and this over here is my x value. So when I write this out, I'm going to say log base of x, log base 3, and then the x, log base 3, the x is 1/27th, and that equals my y value of -3. Okay, so the next type of problems are we're going to evaluate them. So with these ones, what we try to do is we try to set these equal to basically y, set them equal to a value, and then from there we can go ahead and evaluate them. The key to evaluating them, though, is going to be trying to write them in terms of equivalent bases. Okay, and so I'll show you the first one, and you'll see what I mean by that. But if you can do that, then it's easy to solve for the variable. Okay, so evaluate each logarithm. So basically, we want to set these equal to y. So basically, I have log 3 of 27 equals y. All right, now I want to rewrite that into exponential form. So I would take 3 as my base, 3 to the y power equals 27. So if I rewrite it in exponential form, then I'm in good shape. Now, can I rewrite this 27 as with a base of 3 to a certain power? If I can do that, then I'm in business. So on the left side, I have 3 to the y power. On the right side, 27 is actually 3 to the 3rd power. So you can see how I wrote it with the same base. And now if they have exponents with the same base, because of our exponent rules, I can say that these two things are equal because they have the same base. So y equals 3. Okay, so let's try that again here. So if I take this log base 5, square root of 5, equal to y, now I want to rewrite that into exponential form. So if I do that, it's going to be 5 to the y, right? Take my base and take my exponent, equals the square root of 5. Okay, so again, can I write this in terms of the base of 5? I sure can. I've got 5 to the y equals, well, what's the square root of 5? Well, that's the same as saying 5 to the 1/2 power. So from there, because I have the same bases, I can say that y equals 1/2. All right. Finally, the last one. So again, if I set this equal to y, I go log base 2 of 1/32 equals y. If I rewrite that in exponential form, it would be the base 2 to the exponent y equals 1/32. And now, again, can I write this in with the same base number? Can I express this in terms of 2 to a certain power? I can. Remember, 2 to the 5th power is 32. So this would actually be 2 to the negative 5th power because it's in the fraction form. If you can remember that, then you're in business. You got bases of 2 now, so I know that y equals negative 5. Okay, we are cruising. All right, so now let's look at basic properties of logarithms. So, a couple things to keep in mind here. I know you have to write these down, so pause, do whatever you need to do. But again, if we have b greater than 0, and b is not equal to 1, because that's going to just change our answers to 1, 0 every time, and x is a real number, then we know that these things are true. Log base b of 1 equals 0. We also know that log base b of b equals 1. So we'll use these to kind of help things out. Obviously, there's going to be different numbers for b and x. So we can use these to kind of help certain problems later on. We also know that log base b of b to the x power equals x. Just keep in mind there, what you see is you've got a log base b, and then the actual base is b as well to the x power. And then finally, if we have b to the log base bx power, then that's going to equal x as long as x is greater than 0. So if you have it to a power here, then there's going to equal x as well. These last two are pretty similar in how they're written, but just one's just the power, one is the multiplied by the base b. All right, so let's evaluate these and take a look at what we can do. Okay, so if I take log base 5 of 125, well, can I write that to, can I make an equivalent expression, right? Something that's equal to it. Okay, well, I know 125 has a, is a power of 5, right? It's an exponent of 5. So if I can write log base 5 of 5 to the 3rd power, okay? In that case, right, 5 to the 3rd power is 125. So these are the equivalent expressions. But now if I look up at this thing and I can see that this looks similar to this property right here, right? I have a log of b to the x. So I have log base 5 to the x basically. So now I know that my answer here would have to be the exponent 3 because I have a base that's the same as the number I'm taking the log of, log base 5 of 5. Okay, so that'd be the exponent there. All right, so let's take a look at another one. So in this case, I have 12. Now this one is tricky, right? Because to the log power, right, of base 12. So very similar to what we saw, log base 12 of 4.7 power. So this one looks very similar to what we see right here, right? You've got a base of 12, log base 12, and you've got 12 out in front. Those are the same, like right here, okay? So we know that this is going to be equal to the exponent as well up there, or the x value, which is 4.7, just looking at those properties. All right, so keeping rolling here. Common logarithm. So we have, this is a common logarithm, is a logarithm with a base 10 or a log 10. So sometimes we write that without the base. We don't really say anything about the base because it's a super common one. So if you see log x, that basically means log base 10x. Okay, it's a very common one. And then a lot of these properties end up being the same, right? They're very similar to what we saw up here. Or these properties are very similar to what we have right here. Okay? Log base 10 of 1 equals 0. log base 10 of 10 is 1. Log of 10 to the x equals x, and 10 to the log x power would be x as well. Notice that these two here are inverse properties of one another. So sometimes we can do this by just common logarithms can be evaluated using those properties, and we can approximate their values by just punching in real numbers. Now, if there is one of these properties here that works, well, we'll use them, right? If one of these properties up here is good, we'll use them. If not, we can use the calculator by using the LOG button on the calculator, log. Okay, so let's continue with that then. So if we evaluate these expressions, log 14, so log base 10 of 14, so we don't really have a, one of those properties doesn't necessarily hold true here, so we can just punch it in our calculator, and we can say it'd be about 1.14. Okay. Now, log to the 10,000 power, that one we actually can use one of the properties above, because we can say this is log of 10 to the 4th power. And even if you used your calculator and punched in log of 10,000, it's going to give you 4, but we can shortcut that and not even need to punch in the calculator, because we could say this property here, right? Log of 10 to the x equals x. This is 10 to the 4th power, that equals 4. Same thing here, right? We can kind of use the same idea in this one, because we can rewrite this of log of 0.001 is basically log of 10 to the negative 3 power, right? Be ready to know your negative exponents are basically decimals and fractions. So now I know that this is going to be negative 3. For that same reason, same property right here. 10 to the x equals x with a log. And then finally, this one here, we don't have a special thing for it, but I guess what we'd say is x has to be greater than 0, which it's not. So there would be no solution here. So I guess there is a special case here. Remember, x has to be greater than 0. So we have nothing, no solution there. All right, let's move on to natural logarithms, and then we'll be just about ready to be done here. Okay, so on this one, this is a logarithm with a base e or log e. And we denote them with the ln symbol, as in natural log. Okay, natural log. So it has a base e or log. So your basic properties here, very similar, right? Log of 1 equals 0, natural log, I should say. Natural log of 1 equals 0, natural log of e equals 1, natural log of e to the x would be x, and the natural log of e to the e to the natural log of x power would equal x as well. All right, so let's evaluate these. Same thing, we can use these properties up here if we needed to, okay, if that helps. But we can also use the calculator by using the ln button in our calculator there for natural logs. All right, so let's do it. When we go for it, this one, first one, not really anything we can do here, so just use the calculator button to punch in the natural log of 32, and you get about, I think, 3.47 using your calculator. All right, number 11, we can look and say this is e to the natural log 4 power. So that is going to be this property up here. So I know right away that this is going to be 4, because e to the natural log of something is the something, it's in the power exponent. Number 12. Okay, can I write this another way, right? So I can say, sure, I can say this is the natural log of e to the negative 3 power, right? So if I do that, then I know that it's negative 3, because right here. Natural log of e to the x equals x. So we're good on that one. And then finally, we would use our calculator on this one as well. Just punch in the ln button here on the calculator, and it would be the negative of that. So it would be negative 2.20 about, with rounding to the nearest hundredth. All right, how are we doing on time? Where are we at on graphing? Wow, long sections. Okay, so let's take a look at the graphing, and then we'll kind of go through it. Now, I want to rewrite this. I don't like the way that this is written, so I'm going to cross this out and write something else here, okay? All right, so first thing you want to do is you want to rewrite this in the function using the rules of logarithms. Now, remember that these are inverses of each other. Remember, the inverse and logarithm is an inverse of an exponential form and vice versa. So we can rewrite it in that form. Then I want you to make a table. Number 2, to me, is make a table for the inverse function. Okay, so just make an XY table for the inverse function, which would be an exponential function. And then finally, the third thing, well, not necessarily the third thing, would be number 3, switch your X and Y's because it's an inverse, I can just switch those values. I know what inverse is over the line y equals x, so I can just swap my X and Y's, and I'm good. And then the last thing would be my plot my new points. Okay, so taking a look at the graph. So if I take f of x equals log of 2x, so my first thing is to rewrite it as the inverse. Okay, rewrite the function using the rule of logarithms, which means it's an inverse. So that's going back to the first thing we talked about, our definition. So this is the inverse of this. So basically I want to put it in a f of x equals beta x form. So I do so by, I'm going to just take this and say, well, if I write it as the inverse, this would actually be, I should say f of x. F of x equals 2 to the x power, because that's the inverse of that function. Okay, so now if I make a table for that inverse, what I'm going to have is, if I just pick some select numbers, right, 0, 1, -1, 2, -2. Okay, if I do that, if I plug in 0, I'm going to get 1. If I plug in 1, I'm going to get 2. -1 is going to give me 1/2 or 0.5. 2 is going to give me 4, and I'm going to have 1/4 or 0.25 or 2. Now that is my inverse function. So that's the exponential function, which we know our exponential function, this would have a graph that kind of looks like this, right? So, and if we just kind of picture that on there, remember we're going to reflect over this line, we should have something else. So now what I'm going to do is I'm basically swapping these out. I'm going to swap these out, and my new x, basically of the inverse, so the log function here, I'm just going to switch these up. So I would be 1, 0, and 2, 1, and 1/2 and -1, and 4 and 2, and 1/4 and -2. So now when I graph those over here, I can say x is 1, y is 0. Just be careful with my scale there. I'm sorry. X is 1, y is 0. X is 2, y is 1. Just put me here. X is 1/2. And I'm going to be down at -1. X is 4, y is 2. And then x is 1/4 way down at -2 here. So now my new graph is going to look like this. Okay? So notice that this graph here would be the inverse of that because it would be flipped over, and that graph would kind of look like this up here. So we're just kind of thinking that they're the inverse of each other. Okay? So you can see that it works out according to this action right here. Okay, so let's do the second one and then let's be done for the day. Okay, so the first thing I want to do is I want to rewrite this in terms of an inverse. So I want to go f of x equals 1/3 to the x power, right? That would be the inverse function of this. That'd be the exponential function. Okay, I guess the inverse. And then if I plot points based on this one, so again, if I just give my 0, -1, 1, 2, -2, let's go quickly so you can see, but these values would be what I would put in. Okay, and now if I swap the x and y's, right? If I switch these around now, I just put these here, and my y's become my x's, or my x's become my y's. And now I can graph here what it would look like. So 1 and 0, 3 and -1. It gets a little bit tricky to think about that because you're not really going in order. 1/3 and 1. 1/9 and 2, so it's even closer. And then 9 and -2. Now I don't even have a 9 on here. So it would be down here, 7, 8, 9. So my graph would look like this. All right, so that is 3-2. I know it was long and there was a lot to it, but that's it. Bring your questions.